All right, welcome to the first seminar of Physics 8224, Exploring Black Holes, Astrophysics and Cosmology, General Relativity. My name is Edwin Taylor, and with us tonight is Kristin Burgess, who was the section leader, the recitation teacher last time we offered the course. Ed Birchinger is ill today and phoned in that he was not going to be able to come, and so I asked Kristin to work with us tonight. She's a cosmologist graduate student, and so what's going to happen tonight, this is a good opportunity for you to begin to probe the things you may want to go into more deeply when you get into the projects. What we're going to do is write big on the blackboard your questions, and we'll fill the blackboard or until you run dry. And then Kristin will take cosmology and I'll take black holes, and we'll see whether we can put together a connected talk that will answer some of your questions. So we're putting ourselves on the line here. And no doubt for some of your questions, the answer will be, I don't have a clue. And that's part of what we're here for, is to admit our ignorance. So
well, I think also perhaps the point is more to get the questions out on the table and start thinking about these things. I guess you have to hand in soon possible project research topics. So here's a time to start asking questions if you don't even know what something is, or want to know a little more about it, or want to know if the thing you saw on Star Trek is really physics, or, I mean, anything is fair game. So
who's first?
Does anybody have a question about the universe? Has anybody looked at any of the topics yet for projects at the end of the semester? Anything look particularly interesting?
Yes.
I'm wondering about the idea that if matter can or cannot escape from black holes at all.
The question, I'm going to repeat the questions because you don't have a mic. She's wondering about the question of whether or not matter can escape from a black hole. I want to line up all these questions and then we'll sort them out. Yes?
I was wondering whether you can talk more about Hawking's radiation.
Sorry,
Hawking.
what is Hawking radiation?
Yes.
Or is there a more
I think
specific
we had,
question?
a very brief introduction to sort of the basic ideas of what it is, and it sounded quite interesting. So I was just wondering whether you can talk more about
So
that.
tell us more about
Okay.
Hawking radiation. Are you from Cambridge? All right. See, these two people are from Cambridge, and that's where. Oh, three of you. Okay. And
I was wondering about gravitational waves and what the current ways are for trying to detect them, and what the current ideas for detecting gravitational waves are without having some big cosmological catastrophe happen somewhere else.
So what if I were to say, what is gravitational radiation and how do we detect it? Is that your question? Or do you want to? I got to fit it in that much board,
right.
so.
I don't know. That's your job. Not only, like, how do we detect it? How are we trying to detect it now? But, like,
what produces it in the first place?
Yes, and what ways we're thinking about detecting it in the future, not just ways we're trying to do now.
Okay.
so it's LIGO and LISA and all
Maybe
that
I'll
stuff.
turn that into two questions, if that's okay. So one is, what produces gravitational radiation? Because that's a good question. And two is, how are we detecting it now, and what are the future prospects?
Right.
Okay. You gotta not move on to the next one quite yet here.
supermassive black holes and just regular black holes besides the mass difference? Like how that makes that from different from each other?
Okay. What's super
Supermassive.
about a supermassive
Yeah.
black hole? Okay.
How fast does gravity travel?
Okay. Great. So
How fast does gravity travel? That's a good way to phrase it.
do we want to refine it like how fast does gravitational interaction propagate, or do you want to just leave it as how fast does gravity travel?
Well, I was thinking like how fast gravitational, like the interaction propagate.
Okay. Well,
You can phrase it as
That's
Okay.
fine. How fast does gravitational interaction propagate? I think that's a great question.
I heard that the black hole near, in the sense of the Milky Way, our galaxy was unusual in that it was less luminous or something. Is that right? And how is that
Yeah.
unusual?
Essentially, why is the black hole in the middle of our galaxy not as luminous as it ought to be?
okay.
What is inside a black hole?
Good. All right. What are the reports from inside a black hole? Yes.
Do all galaxies have black holes in them?
Great. All right. So yeah, sorry. The last one is what is inside a black hole, and then do all galaxies have black holes in the center?
Are there actually non-spinning black holes, and if so, why aren't they spinning?
Do all black holes spin and why? Or
Are there any non-spinning black holes, or is it an empty set?
okay.
I saw somebody's hand. Austin, did you have a
Well,
question?
it's a little bit the same as number 8, but what do we know about space-time beyond the
Sorry, what was
To
it?
number 8, you can add, what do we know about space-time inside the horizon?
Okay.
You could just put space-time inside the horizon. There. Your turn, yes.
What evidence do you actually have for the existence of black holes?
Great.
I'll be back to you. Yeah.
Apart from at the end of the lives of massive stars, how do black holes form, such like primordial black holes?
Okay. So right, how do black holes form? Can I just leave it at that, and we'll get into the details when we talk about it?
What effects does frame dragging have on the matter around the black hole?
Okay, great. So yeah, just what effects does frame dragging?
Frame dragging, question mark.
Okay.
do they exist? Is there anything being done to find them? How might they be detected?
Primordial black holes, how do they exist and how would we find out if they do? Primordial just means from the beginning. Austin?
What's the connection between black holes and the Big Bang singularity?
Sorry, what was the last question?
15 is, what is the connection between black holes now and the Big Bang, or the initial singularity?
Okay.
Of gamma ray bursters.
Say that again.
The causes of gamma ray bursters.
What are the causes of gamma ray bursters? You answer that and you'll be famous.
What does quantum mechanics have to say about black holes?
Great question. What does quantum mechanics have to say about black holes?
Again, answer that and you'll be famous.
These are great questions. Yeah.
What was
We're
the-
getting near the end. 18, the relation between information and black holes.
Can you guys still see it down there? Yeah? Okay. Sorry.
The relation between information in black holes and entropy in black holes.
What is the entropy information paradox?
Whatever. We'll make up a question out of the ideas.
Going along the lines of the theory that black holes are portals into other universes, wouldn't presumably something going into a black hole in another universe maybe wind up here?
Can you use a black hole to travel to other universes? Is that?
No, she's asking the reverse question. Could someone in another universe travel into ours through a black hole?
Okay.
So let's just say black hole universe travel, and we'll talk
Okay.
Sounds good.
Okay, we got a couple more. What's bugging you that you haven't given us yet?
Do you guys have questions about the Big Bang and the origins of the universe, or about what we know today about the size of the universe, or yeah?
What was before the Big Bang?
Okay. So the question is, what was before the Big Bang?
Does the universe wrap back on itself?
Okay, so the question is, does the universe wrap back on itself?
If we look far enough away, would it be theoretically possible to see the Big Bang, and would it be in one direction, or?
That's the best we can do.
That's a
All right,
great.
we'll
No,
talk about
that's a
that.
great. That's a great question.
Can
If we
we
look far enough out, can we see the Big Bang, and in which direction would it be? I think that's about it.
Well, I mean, we could keep going below here. You guys probably have more questions, right? Last year we had 40, so I think.
Yes, but we didn't have to write big last year.
Why don't we just keep going? And it's okay if we have to cover some up because we can always pull the blackboard back down. So sorry about the non-linearity here, but I'm going to start below here. So we got up to 22.
Can we talk more about dark matter?
Okay, so how about just what is dark matter?
Well, I know that it's like matter you don't see, and that it constitutes most of the mass in the universe compared to what we can see, and so like the theory, right?
Okay, explain dark matter. Again, do that and you'll be famous.
Well, it isn't. It's partly that, and partly you're asking the questions right at the edge. That's what's. You're up to date. I mean, it's great to have those questions.
There was one.
What was space-time like in the universe before atoms were formed, like in that time?
What was space-time like before atoms?
Yes.
Okay. All right, in the corner.
Is it possible for a black hole to pinch off and form another universe?
Great. So can a black hole pinch off and form another universe?
What would happen if two black holes collided?
Great. So what would happen if two black holes collide?
Can you come down a little so that maybe the camera can't see where that shadow is?
Okay. To 27. Mm-hmm.
If one made a black hole in a laboratory, how would one theoretically contain it?
How about just can you make a black hole in the lab?
Okay.
All right.
What's the science fiction story about people who arrive on Mars and there's a black hole held in a somehow, and they turn it off and the black hole starts oscillating through Mars, and every time it goes through it makes a hole. So pretty soon Mars is just like a Swiss cheese and it collapses. That's science fiction, but it's, if, you know, given the situation, that's probably what would happen.
Okay, how do you make it and what do you store it in?
There was another one. Austin?
Is there a center to our universe?
Great. Is there a center of the universe?
Okay, what I suggest we...
Wait, I think we got to give them a little more time. Some people haven't asked any questions yet.
Will the universe stop expanding?
Ah, that's a great question. So yeah, will the universe stop expanding? Mm-hmm.
What's the shape of the universe?
Oh, great. What's the shape of the universe? Those two might be related. Any more? Yeah?
What do we learn by examining peculiar geometries of space-time? Like I've heard about somebody taking a model of the universe where it was actually, space-time was actually pinched in the middle between, you had two lobes of the pinch in the middle. What do you gain by studying that?
Okay. So how about if the question is,
How do you...
what do we learn from strange geometries of the universe? Does anybody want to know anything more about the cosmic microwave background radiation? Sure. All right, I guess I walked into that. All right, I'll just write CMB question mark. Yeah?
What is the universe expanding into?
That's good. What is the universe expanding into?
You can add it on the line, make it 33 under that.
Okay. Is there anyone who hasn't gotten to ask a question yet? Do you have anything you want to add? We can squeeze a few more on.
What I suggest we do is to start in the large scale, and you can take those questions having to do with cosmology and say something about each one. We will obviously not answer all of these in detail, and one of the major purposes of this exercise is so you can see with each other what a rich subject this is and how many things there will be to study, all of which we won't cover even in this class, but life goes on. You want to start?
Sure. So I guess, maybe I would just start by talking about our picture of the universe as a whole, just because some people had some questions about things like the center of it and what's it expanding into and everything. There isn't a center to the universe. And the example that people always give is, imagine you were, say, an ant walking on the surface of a balloon, or something perfectly spherical even. Nothing looks like the center to you. You can't leave the surface, so you can't talk about inside the balloon. And as the universe expands, and this sphere just gets bigger and bigger, everything is moving away from you, but there's still no center. But in fact, from any point on the surface, it would look like everything was moving away from you. So everybody sort of thinks they're at the center. Like here in our galaxy, we see everything else receding from us. But it's not, because we're somehow magically at the center. Does that make sense? Do you have a question?
Question of it, but then how did it all come from one place?
Well, so imagine that this balloon is shrinking down and getting smaller and smaller and smaller as you go back in time. And originally, it just sort of all started from one point. At the very, very beginning of the universe is actually a pretty complicated thing. In fact, inflation, which is one of the things I'm doing my thesis on, is one of the theories that tries to talk about this. Of course, you don't really want a model where everything is infinite at the very beginning. But say right after the very beginning, things can be very, very, very small and dense and hot, but not actually infinite, and then expand from there. Does that make sense? So then what does that mean it's expanding into? Does anybody have any ideas? What do you think? So, what about this balloon? As I'm blowing the balloon up to the ant who's on the surface of the balloon and can never leave the surface, as the balloon expands, what is it expanding into? The ant can't really answer that question, can it? It's sort of like the expansion of the universe is creating space-time itself. So it's not like you can point to something and say, that's outside the universe, and now it's in the universe, or whatever. These become pretty hard and maybe even philosophical questions. Does that Does that seem reasonable? Is anybody not satisfied with that answer? What were some of the other questions about that were related to this? So maybe we can even talk about, will the universe stop expanding? So this is something that you will definitely get into later in the course, and I'm not going to probably spend a whole lot of time talking about it now. So you'll probably have homework about it and everything. But there are actually a couple of different possibilities for the future of the universe, and it depends on what the universe is made up of now. So what the density is of matter and other strange things. And it's possible that it could expand forever. It's possible that it could stop expanding and shrink back down and collapse in a big crunch. And we don't know. So that's maybe not a very satisfying answer, but yeah?
Can I just ask in relation to that, what's kind of negative energy or negative gravity? Like, people talk about this.
Yeah, so
like the cosmological concept.
right, so there's normal matter, which is pretty much everything you guys are familiar with. And then there's this stuff called vacuum energy or dark energy or a cosmological constant, or it has a lot of other strange names. And it doesn't behave at all like normal matter does. And in fact, it causes the expansion of the universe to speed up instead of slow down. So if you imagine you just had a universe made of the kind of matter you're familiar with, and it was expanding, over time gravity would kind of be slowing down this expansion, pulling everything back together. And you would imagine that long enough in the future, the expansion would stop. So cosmological constant has sort of the opposite effect, and it actually makes the expansion speed up. And we'll talk about that later in the course. All right. Do you want to pick something?
What's inside a black hole? What do we know about space-time there? You have to decide what kind of theory you're going to bring to bear on that question. If it's general relativity, that's called a classical theory. There's no quantum mechanics in it. And we have equations that we think can be extrapolated inside the horizon. When we do, of course, no one, according to that theory, no one can go inside the horizon and come out again. Once you go inside, your radially inward motion takes on the same inevitability that time does for you. You're young, I'm old. That's inevitable. The only alternative is not as pleasant. And the same inevitability happens according to the classical theory. Now, there's some detail to this which is quite interesting. When a black hole forms, we talked about two black holes colliding. When two black holes collide and coalesce and make a single black hole, a huge amount of energy is given off in the form of gravitational radiation. But once that new black hole is formed, there is also gravitational radiation inside. And we don't know what happens to that. It reverberates just like a sound inside a sphere. And you will read some in Exploring Black Holes about what's called egg beater space-time. If it's a young black hole, there is some chance that if you fall into it, you'll just be ripped apart because of these chaotic gravitational waves that are inside. There is some evidence that if you wait long enough, things will calm down, but they really don't know about that. As Ed Birchinger said last time, if you have a spinning black hole, then the singularity in the middle is a ring. And the spinning black hole has some other interesting features. There's an outer horizon, then there's an inner horizon. And once again, there is some theory, there is some theoretical work that tells you that the metric that deals with the spinning black hole, the so-called Kerr metric, is okay between the outer horizon and the inner horizon, but as you get to the inner horizon, you get into a chaotic region. This is of some real interest to a lot of people, because if you can make it through that chaotic inner horizon, you might be able to get to the ring in the middle, and goodness knows what you might be able to do. appear in another universe, go backward in time, who knows? So once we get inside the horizon, we have a very interesting situation because there are many possibilities that can be worked on theoretically, some of which sound like science fiction, and indeed is science fiction at the minute because there's no way to publish the results of doing an experiment, at least outside the horizon. Inside, you could have a little community that would ride inward and communicate with each other. What was space-time like before atoms? Well, I'll leave that to you, but let's see.
So when we talk about that now, space-time doesn't really have anything to do with atoms. I mean, so if you think about what atoms are made of, they're made out of what? Does anybody know what particles go into making atoms? Right, so, but even before you get that small, you have protons and neutrons. And it turns out that protons and neutrons are themselves made of quarks. And there's also electrons, which are themselves fundamental particles. So when the universe was hot enough that essentially the quarks weren't even bound together to form neutrons and protons, there was just this whole hot sea of quarks, that space-time existed, you know, just fine before atoms on their own existed. And even before that, I mean, you could imagine a universe where you just had, say, a whole bunch of photons, and you'd have space-time. Yeah?
What I meant more with that question was when the entire universe was that dense.
Okay, so inflation is this period in the very beginning that's sort of the bang part of the Big Bang. And essentially when inflation ends, the energy that's there goes into sort of the normal fundamental particles that we think of, like quarks and electrons and everything. And it's just this hot soup, and it's very, very dense, but it's there, and space-time exists. I mean, things are squished together a lot relative to the sizes they are today, but maybe I'm still not understanding your question.
And what was space-time like during that inflation period?
That's a little bit of a harder question to answer. We don't have one single accepted model that describes the universe then, and I think it depends on, you know, the particulars. In fact, there are models that have more than 4 dimensions. You know, you may have heard of all this crazy doing cosmology in 5 dimensions or string theory in 11 dimensions or all this stuff, and we just don't know at this point about that. So, were there other questions relating to that?
Primordial black holes. And this will have something to do with Hawking radiation and the relation between quantum mechanics and general relativity. According to general relativity, in a non-rotating black hole, the matter that goes in goes to the center and is crushed to a point. Quantum mechanics forbids this. Quantum mechanics will not allow you even to put a single electron at a point, much less all the debris that may be pouring into a black hole. So one of the beauties of general relativity is it proves its own demise. It cannot work in the center at this singularity point. Although, and we don't have now one of the big, if you say what is one of the biggest questions, it would be what is the relation between general relativity and quantum mechanics? We don't know. We're edging up on it, and Stephen Hawking edged up on it in the following way. There's a paradox which we've also mentioned, which John Wheeler explained to me. You've got a dirty teacup, and you throw it into a black hole. Well, a dirty teacup has disorder in it. It's dirty. You throw it into a black hole, and it's gone. So the disorder in the universe is decreased.
Or the other thing sometimes people say is, what if I take a dictionary and throw it into a black hole? I mean, clearly there's a lot of information in the dictionary, and can I destroy information by throwing it into a black hole?
Right. So there's a sequence of the history of this, which you will be reading in Thorne's book. But one thing Hawking realized is that when you look at a black hole, it is not really black. It is just very, very cold. And it has a temperature. And it emits radiation. And one way to think of this radiation, there are many ways, but one way is that vacuum all around us is not a vacuum. It is a continual virtual particles are being created and rejoined.
So I might just rephrase that a little bit. What really, we just need to revise our definition of vacuum. So there is such thing as a vacuum, but instead of thinking of vacuum as completely, absolutely empty space, you need to think of the vacuum as simply the lowest possible energy density that there is. And it's not zero. So you may know about electron-positron pairs, sort of virtual particles that can be spontaneously created from the vacuum, and then they'll annihilate and disappear again. And this is happening all over. So for a tiny, tiny, tiny bit of time, these particles appear and then go away. But they have gravitational interaction. I mean, they're sort of like, you can think of almost as there being some mass density in the vacuum. And so that's the vacuum. It's just non-zero. So, all right, go ahead.
Oh, fine. And Hawking realized that if you have one of these pairs created very near the horizon, one of them can disappear into the black hole and the other one get away. Now, that one that gets away is a permanent particle now. And so you have the black hole and this additional particle. Now, conservation of energy is something we fight very hard to preserve, and that means that the black hole must have lost energy that appears as in this distant particle. And so the black hole is, and he worked out the formulas, and it turns out that there is a temperature to the black hole. I think it's inversely proportional to its mass. And so as the black hole evaporates, which for a sun-sized black hole would be many times the age of the universe, as it evaporates, it gets smaller in mass, and the temperature goes up, and then it gets smaller, and the temperature goes up, and it radiates more. And at the end, there'll be this huge, who knows, probably a huge bang. So the question about primordial black holes really has to do with how big were they? If they were the size, if they were the mass of baseballs, we know how they would have evolved, and they would have exploded long ago. Then intermediate sizes would be exploding now, and we're looking out. Could this be the basis for the gamma ray bursts? I don't think so, but it might be primordial black holes blowing up or black holes colliding. So the general answer to these questions is we don't have a theory that combines quantum mechanics and black holes. Hawking radiation is kind of edging up on this theory, and one of the consequences was that he and others figured out that the entropy of a black hole is related to its area. So when you throw the teacup into the black hole, the mass goes up, the area, the horizon gets a little bigger, and the disorder in the teacup is still there. So you have not violated thermodynamics.
So with the particle antiparticle, if one of the particles is going into the black hole, why can't that added mass to the black hole, why does that energy not offset the energy of the particle that escapes?
I don't know.
Yeah, I mean, it becomes a little tricky, and I think at this point some of the oversimplified pictures that we use to describe this sort of breakdown. I mean, something that you'll hear, which I personally think is wrong as the explanation, is that you have this particle and antiparticle, and say the particle goes out carrying, its mass m, and the antiparticle goes in, and it sort of like has a negative mass to the black hole. I mean, this is I think not a correct description, but
well, one way to
right, you'd think that they would sort of each happen about the same. This becomes hard to talk about in this language at this point, I'm afraid. I mean, maybe somebody could give you a better answer.
Well, I think you say, here's the initial condition, black hole. Here's the final condition, black hole and faraway particle. Now, a lot of complicated stuff's gone on in the middle, but the beginning situation is clear and the final situation is clear, and I can't describe to you the intermediate situation, and I apologize.
Would the mass of the black hole change when stuff gets sucked in it?
Yes, when matter falls into a black hole, it's like ringing a bell. It'll vibrate a little, then it'll settle down, and the radius of the horizon is 2 times the mass in the units you're learning to use. So when the mass goes up, the radius goes up. And one of Hawking's theorems is the area of the horizon never decreases. Because if it did, the entropy would decrease, since the entropy is related to the area. So when two black holes collide, one of the homework problems you have, two black holes collide, the resulting black hole has a bigger area than the sum of the ones, or at least not less than the sum of the two that collided.
You said it rang like a bell. What sort of frequency and what's oscillating? And what sort of, can you say what a frequency is in that situation? Are you going to put them?
I don't know. Essentially what we talk about is stable structures, and this is an unstable structure. It will radiate. I mean, one part of the story that Thorne tells is, supposing you've got a little mountain on the black hole, what happens to it? I mean, does it grow? Does the black hole explode because it's not stable? Or does the mountain decrease and you end up with a stable structure? The second is true. But the non-equilibrium black hole is described by Einstein's field equations, which are highly nonlinear. One can do a calculation as a general relativist, but the answer is not something you can write down in a formula.
Okay, so as a black hole evaporates, it loses mass, and the mass is related to the radius of the black hole. So it would seem that as it lost mass, it would lose radius, which means the area would decrease.
Yes.
So I don't understand why the area would decrease.
Right. I'm confusing you with two different theories. One is classical general relativity, which says that the area of a black hole never decreases, number one. Number two, we're edging up to a quantum mechanical understanding, relation between general relativity and quantum mechanics. And that edging into it is, Hawking radiation is sort of the first little commando raid into this foreign enemy territory. And he worked through pretty carefully the consequences of Hawking radiation. And the consequences are that a black hole does have a temperature. A big black hole has an immensely small temperature, a little teeny tiny temperature. But it radiates. And a sun-sized one would take 10 to the 80th years to radiate away, or something like that. But a little black hole would radiate like mad. So as the thing radiates away, it gets less massive. Its temperature goes up. It's inversely proportional to mass. The temperature goes up. It radiates faster. Its temperature goes up. Its mass decreases faster. And at the end, it could be a big explosion. That would be a complicated, since that's a changing structure, it would be a complicated calculation.
But essentially the point is just that this whole radiation thing is a quantum mechanical effect.
Yep.
So.
Those approximations for how long it takes for it to radiate away assumes that it's not eating an accretion disk.
Absolutely. That assumes there's nothing being added. And of course, there is everywhere in space atoms and so forth that are raining down on any black hole. So whether the two would come into equilibrium or not, I don't know. It depends on the size and the density and things I have no way of knowing.
So here, should I maybe...
You want to talk about gravitational radiation a little?
Not really. Is there anything under there? No. So I was going to maybe just try to say a little bit more about the CMB. Maybe you think I'm going crazy, but it's just very exciting. So Edwin was explaining a little bit at the very beginning about this, but I think after having talked about this picture of a hot expanding universe and the particles, it maybe will make a little bit more sense. So, I mean, imagine in the very beginning, we're talking the first few 100,000 years. You just have this very, very hot, to be honest, pretty boring soup of stuff. And finally, when it cools down to the point that the electrons and protons can combine to form neutral hydrogen, the universe sort of goes through this phase transition where it goes from ionized charged plasma to neutral to hydrogen. And in the first part, the photons interact strongly with the charged particles, whereas once it becomes neutral hydrogen, they pretty much don't interact anymore with the photons. And all these photons are free streaming and pretty much don't interact with anything until they hit our detector. So, I mean, that's pretty amazing to think of 14 billion years later, for the first thing this photon has touched. But that's how it goes. So this happened everywhere at this certain time in the past. And what we see is that light from this, it's called the surface of last scattering, because it's the last time the photons interacted with the matter. And they decoupled and they've been traveling towards us, and that's what we see. So it's this picture of what the temperature was of the matter on this shell. And that's pretty much the picture. Does anybody have specific questions?
What about all the photons that did interact with stuff before they hit, or didn't hit your detector, rather?
Well, right. So there are many, 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 many photons that we won't see. I mean, and they're just going. There's some going through Edwin right now. Like, they're all over. But the point is, the ones we observe are ones that we had been free streaming since the surface of last scattering, and so we're pretty much the only ones we see are ones that are, you know, giving us this picture of what it looks like.
But are those a representative sample of the original ones?
Yeah, so right, certainly some of them will, you know, hit a galaxy or a star or do other things, but we then just won't see those. But, you know, it's not like there's some big selection effect where we're only seeing some population of the original distribution. I mean, this is the original measurements from the Kobe satellite in the early 90s. There's this gorgeous, gorgeous picture, this sort of famous talk at the annual astronomer conference, where the guy just went up and put this picture down that was the most perfect Maxwell-Boltzmann distribution you've ever seen. And like this curve going right through it, and the error bars were like, I don't know, magnified by 200 times. The line went right through it. And they were just measuring. I mean, it's just the black body formula that you guys all learned about in thermal physics. So, I mean, it really is just rating like a perfect black body. So anyway, I was going to say that's the part that's the same. So at the level of 1 part in 10 to the 5, there are then little fluctuations. And that's sort of where all the interesting physics is.
See, as you've heard this 100 times, as you look outward in space, you're looking backward in time. And there comes a place where the time is 300,000 years after the beginning. And that is a wall of plasma moving, that is moving away from us because the universe is expanding. And we are seeing, and what we see is layers of that are, in a way, how can I say, the light comes from different layers, but each layer is moving away from us so fast that a very high temperature has been reduced to almost 3 degrees, as low as 3 degrees Kelvin. So it's a very interesting view as you look out. And you can't see that radiation because it's microwave, because its typical temperature is 3 degrees.
You can see it. If you don't have cable, if you have a TV with antennas, it's something like a couple % of the static that you see on your TV. I mean, it really is microwaves, and it really is, I mean, in fact, there's a really cool story, which maybe you guys will learn about later in the semester, about the guys who discovered this in the first place. And they were building antennas, and they were trying to get rid of this noise in their antennas. And no matter what they did, they couldn't get rid of it. And they finally figured out, it's not noise in our, I mean, it is. It's a signal in our detector, and it's the same in every direction. And it must be, you know, coming from way out there in the universe.
There's a really interesting human story about that. These were Penzias and Wilson, and they were looking for pigeon droppings and everything in their antenna.
Yeah, they were just going crazy.
And they called up Bernie Burke, who's still here as a physics professor, and they said, we're having this problem. And he said, you should call Robert Dickey, who was at Princeton, because he knew that Robert Dickey and his students were setting up an antenna because they figured there had to be microwave radiation left over from this. So Dickey picked up the phone, and the graduate students were in the other room, all men. He picked up the phone, there was a long talk, and he put it down and said, boys, we've been scooped.
Penzias and Wilson did get the Nobel Prize.
And Dickey didn't.
Eventually, for discovering this. But so the other side effect of all this is that we can't see any farther. This sort of, at least using photons as the method for seeing, we can't see through that wall because the universe is opaque. So once you try to look back farther than the surface of blast scattering, and you have this hot plasma, the photons have a very, very short mean-free path. And so you can't see through it anymore. And so we sort of don't have any hope of using the traditional observation techniques to see, you know, anything about actually the very beginning. So this is the closest you can get to observing the Big Bang.
With light.
With light, yeah.
What is the implication of the 1 part in 10⁵ that's anisotropic?
So essentially that arises from the fact that the universe is not completely homogeneous. So the fact that it looks the same temperature in one direction as the other says something about the universe being isotropic and homogeneous, because they're, you know, otherwise they wouldn't be in thermal equilibrium.
I mean, like, what is the implication of that? Like, I know that, you know, the fact that it's so homogeneous, like,
right, so
that little part, what does
yeah.
that mean?
So what the little part on top of that is saying that it's not perfectly homogeneous. There's little ripples in the density. So if you were to measure sort of the local density of matter in the universe, it's not perfectly smooth. In fact, there were sort of these slight ripples in the very beginning that then through gravitational interaction grew, and that's what formed galaxies eventually. So sort of the progenitors of what would become galaxies were these little tiny ripples. In fact, inflation predicts exactly these ripples, and it's in fact quantum fluctuations that get blown up during inflation, you know, sort of inflated to these large length scales. And then, like, you know, over billions of years, they amplify, because you can imagine if it's a little bit more dense in one place than nearby, that'll have a stronger gravitational pull, and so it'll get even more dense. And I mean, this is what formed large-scale structure in the universe. So looking at the anisotropy back at 300,000 years when we see the CMB gives us a picture of what the sort of the large-scale structure was at that time. And so, you know, people do things like numerical simulations of if you started with that level of fluctuations in the density and try to evolve forward using the physics that we think governs all of this, do you end up with a universe that looks like the universe we see around ourselves today? So the parameters that come into this are like, you know, first of all, of course, the temperature of the CMB, but also things like the expansion rate of the universe, and also the derivative of the expansion rate, or sort of the acceleration. What fraction of the matter is bearing out? So, I mean, there's sort of a lot of things that will influence this spectrum of perturbations. And in fact, like almost all of cosmology turns out to be encoded in the spectrum.
Now, supposing you want to look back farther, what messengers can you use? Well, neutrinos would be a possibility, because they would go through a plasma. Another possibility is gravitational waves. So let's talk a little bit about gravity, which Kristin doesn't want to, and I will do as best I can. Gravitational waves are stretching and shrinking of the fabric of space-time itself. And if you ask how much, well, first of all, Taylor and Hulls, who got the Nobel Prize, as Birchinger mentioned last time, for showing that a neutron pair that's circling each other, one of which we can see because it's a pulsar, or observe, that the radius between them is shrinking at exactly the rate that they know a tremendous amount about these orbits, all the gravitational general relativity effects and so forth. And they can calculate what the radiation ought to be for gravitational radiation. And that energy that's given off in gravitational radiation is lost from the orbital energy, so that one can predict how, given all the parameters that they know very well, at what rate this orbital radius should be changing, and it works perfectly. And so that is considered to be it could be something else, but the fact that it's perfectly predicted, given what they know, is itself strong evidence that gravitational waves exist. MIT is, with Caltech and others, is setting up 2 gravitational wave detectors, one in Hanford, Washington, one in Louisiana. And they need two because essentially what they are two arms of interferometers, and they're going to measure the small change between two masses that are hung as pendula as the gravitational waves go over.
The baseline here is like 4 kilometers. I mean, it's huge.
And they can detect the waves falling, striking the Pacific coast. And a truck going by is like an explosion.
The joke is they measured halftime during the Super Bowl in Louisiana because everybody went and flushed the toilet, and it actually made enough of a signal, like all the water running through the plumbing, that they measured it in the detector.
So that is why they have to have two, because if they detect something in Hanover, they want to be sure it isn't people flushing toilets. And of course, during the Super Bowl, that's probably happening both places.
Well, no, but I mean, the fact is that you can calculate what the time delay should be between seeing the signal in one detector and seeing the signal, whatever it is, 4,000 kilometers away in the other. And if it was something like a big earthquake that actually affected both, the time delay between the signals would be very different than if it were a gravitational wave or the Super Bowl or whatever. But I mean, this detector, imagine 4 kilometers apart, two masses with a little mirror on the end, and shining a laser back and forth, that sort of bounced from one mirror to the next, and being able to detect these two things getting closer together or farther apart by less than a wavelength. I mean, that's the sensitivity of this detector. So it's amazing to me that this works.
And so they have there's only one gravitational source that they can predict pretty carefully, and that is two orbiting a binary system that finally coalesces. They have a pretty good way of predicting how much gravitational energy would be given off by that. Everything else is kind of a guess. And so they've set up these detectors because of the length and the frequency of the hanging masses and so forth. They've got the maximum sensitivity at about 100 cycles. And they've set it up so if they're lucky and they turn it on, they will detect some things, but they may not. And then there's a second generation and so forth. And there's other people in Europe who are working on it. They ultimately would like to put these interferometers into orbit, and there's a planning going on for a system called LISA, L-I-S-A, LISA. And it would involve a triangular setup that would be run behind the Earth and would be 1,000 kilometers on a side or 10,000 kilometers or something incredible.
It's pretty ambitious.
Yes. But of course, it would be far from the trucks and the Super Bowl. That would be the good news. The bad news is it would be way out there, and it's very hard to maintain. You can't send a shuttle up to work on it.
Yeah, pretty much once you deploy this thing, you don't get to touch it again.
But Bertschinger has said to me that he thinks this is as important a development as the development of the telescope, because it's a whole, that as soon as you get a signal, you're going to find things that it never would have occurred to you before. And they'll get better. And as they get better, more and more things will become, we expect. If you can predict what you're going to see, then you know when you should get a signal. But once you get a signal, you're going to find things that you had no idea about.
Something that we maybe didn't say, but the gravitational radiation does propagate at the speed of light. So the same as electromagnetic radiation.
Do we believe this radiation is quantized?
Yes. I mean, I guess, is the photon a wave or a particle?
Are you guessing
What are, so, I mean, if you, say, look at this from quantum field theory perspective, all of the things that are normally particles then become fields in this theory. And, sure, people talk about the graviton field. And it really is, much like what you might think of as, the photon field. What's a particle like a photon in many regards? I mean, it's a particle that has, well, let me not get too far into it, but, I mean, we don't have a full theory of, quantum field theory with gravity all, happily working together. So that's a pretty hard question to answer.
You want to talk about whether all galaxies have black holes?
That's a pretty, just from a logic point of view. I don't know how you want to answer that. I mean, have we seen a black hole in the center of every single galaxy that we've seen? Well, no, of course not. But that doesn't mean they're not there. It's actually, I mean, how would you guys imagine you'd even go about detecting a black hole in the center of a galaxy? Can't see it, it's black. Does anybody have any ideas what you'd do? You mean
Gravitational lensing?
Yeah, so gravitational lensing, I think, works great if you have, say, empty space, a black hole, a source behind it, and you can see it or something. You got to remember, in the center of a galaxy, if we're really talking about black holes in the centers of galaxies, it's, there's a bunch of crud surrounding it. And in fact, probably opaque crud that you can't even see through, because there's this whole big accretion disk, full of dust and everything. And it's very, I don't know. You can't, I mean, if you look towards the center of our galaxy, you see dust. You can't see all the way there. So, I mean, that's a little bit of a harder way, I think. Yeah?
The orbits of stars close to the centre, and if they're going fast enough, you've got to have a big mass in the centre.
Yeah, pretty much what you try to do is you try to calculate, so for, say, a star at a given orbit, or at a given radius orbiting, you can just use, the laws of physics to say what the mass must be, providing the central gravitational potential for, a certain orbit to be traveling, at the radius it is. And it's more mass than, I mean, if you put that much mass in a size of that radius, it would be a black hole. So, I mean, what they actually do is look at the Doppler shift. So, as you imagine looking, say, you're lucky enough to look edge on, and you had a black hole, and then some stuff traveling around it. The stuff that's on this side is going to be traveling away from you, so it's redshifted, and then it's coming this side, it's traveling towards you, so it's blue shifted. So you can get the relative velocity of the stuff traveling around. And yeah, when you just do the calculation, the amount of mass you need in the center to sustain an orbit is enough to be a black hole.
That does raise a very important question, though, and that is, you say how you detect a black hole, and I think Kristin has said it correctly. You look at the orbits around it, and you say, well, this has got 2.5 million suns mass. It's got to be a black hole. You'll notice there's a little skip in logic there. The thing in the middle surely has 2.5 million times the sun's mass. But I know respectable physicists, I think I'm correctly representing him, Phil Morrison, does not believe in black holes. Why not? Because he says general relativity has been proven in situations in which the gravitational effects are not terribly huge. That's where we know it works. But it has not been demonstrated, he would say, for extremely high curvatures. And all we know from this evidence is that there's something in there that's 2.5 million times the mass of the sun. But we don't know there's a horizon. We don't know that there's a ring singularity at the center. We don't know it's got an inner and outer horizon and all that business. The Kerr metric, which has been set up for the rotating black hole, we assume that the black hole exists. And a lot of the early reading you do in the Thorne book talks about how Chandrasekhar and others showed that a white dwarf cannot maintain itself against the gravitational forces if it's more than 1.4 times the mass of the sun. And then you go to the next stage, which is the neutron star, and we know something about that. And then the next stage is the black hole if it continues to accumulate mass. But black holes are not things that we can just look at and say, yeah, well, of course, there it is. And sure enough, down near the middle, there's the horizon and so forth. All we know for sure is that if our theories are correct, there's a black hole in the center of our galaxy. If Phil Morrison's right, there may be something with 2.5 million times the mass of the sun, but it's not a black hole, it's something else because the theory doesn't work. Now, part of what you'll read about in Thorne's book is a bet between Hawking and Kip Thorne Hawking, to make life interesting, bet there wasn't a black hole. And he finally gave in and sent the reward that they had agreed on, which I won't tell you about in polite company.
So I want to ask you guys a question, which will lead in maybe to the answer to one of these. What do you think would happen to, say, the orbit of the Earth if I took the sun and replaced it with a black hole that has exactly the same mass as our sun? What would happen to the orbit of the Earth? Exactly. So people, I think, have a sort of common misconception that anything that's a black hole sort of sucks matter in, and you can't help but fall towards a black hole. Well, I mean, that's only true in so much as it's true that anything with a gravitational potential will try to attract matter. And the fact is we have angular momentum and we're in this orbit, and so nothing. So how does that mean I could, say, contain a black hole if I made one in the lab? I mean, what's different about it being a black hole? So say I make a, you know, I don't know, 1 kilogram black hole in the lab. Does that mean that I can just put it in a box, or what do you guys think that the issues are? Yeah?
Well, we were talking about the Hawking radiation earlier, about it evaporating away and exploding. And
all right, so
really interesting.
Yeah, I mean, I guess maybe who knows what would really happen. I guess the thing I was trying to get at is, say I have a 1 kilogram baseball and a 1 kilogram black hole. If you were to calculate what the Schwarzschild radius is for this, it's well inside the outside surface of the baseball. So I can't, like, stick my finger through the event horizon because there's a baseball in the way. And in fact, by the time I got to that radius, most of the mass would be outside, and so it's not actually a black hole. You know, it's not. No one piece of it is dense enough to have enough mass within that radius. Whereas if I had the 1 kilogram black hole, I maybe could stick my finger through the event horizon, and I don't know. I wouldn't want to do it, but.
There was a really interesting question about why it is true that the black hole at the center of our universe is not emitting radiation, is not making its presence known as much as black holes in some other galaxies that we've looked at. You must understand that when a black hole is formed, quite often it's formed by a star collapsing, not one that big, but a lot of stuff is blown off. And then if it begins to accumulate, and pretty soon it's eaten up all the stuff in the vicinity, right? As she said, everything else is going to, if it's far enough away, if you get close enough to a black hole, you do get sucked in. And this is something you will deal with when we get to chapter 4 about orbits. 4, yes.
Well, I mean, it's not so much a matter of how close, but whether or not, say, you have enough angular momentum to sustain you in some orbit outside it versus, you know. But
you cannot have a stable orbit inside 6 times the radius, 6m. So what's probably, and they have detected some little emissions as if some blob of stuff has cycled into the black hole at the center of the galaxy. But it's not a steady beam because it's eaten up all the things that are nearby. And our galaxy's old enough so that it's not running into things that it gobbles up and
I mean, in
creates...
fact, a big black hole in the center of, say, a galaxy that has some huge accretion disk with a lot of stuff falling in is a tremendous source of energy. I mean, it will radiate, it will emit a whole lot of photons as this stuff is falling in. So, I mean, it's certainly not the case that you should always think of a black hole as black. Well, it's only a black hole on its own without anything falling in. Oh, the other thing I was going to say about when we were talking about black holes in the centers of galaxies, we should probably be honest that we're not entirely sure how galaxies form. I mean, this is a current topic in astrophysics research, and certainly there's a lot of stuff about galaxies that we do understand. But, you know, some people talk about whether maybe the black holes existed first and they seeded galaxy formation. Sort of you had a black hole and that's what caused everything else to, you know, come and assemble around it. Or is it the other way around? You have a galaxy and so then it's this big strong potential and so then the stuff falls to the center and that's how you get a black hole. And I mean, there are a lot of theories out there about all of this stuff, but maybe we'll talk about some of that later in the semester.
I'll talk a little bit about frame dragging, and you might want to talk about the gamma ray bursters. A rotating black hole one way of thinking of it is it carries space-time around with it in some sense. To put it another way, if you drop something from a distance with zero angular momentum toward a rotating black hole, it will come in and start going around like this before it crosses the horizon. At every point in that orbit, it has zero angular momentum. So even though it's you might say, circulating around the black hole, space-time itself is, one way of speaking, is circulating. And so it's at rest with the local space-time. The analogy is like a tornado, but it's not a terribly good analogy. If you want to go straight into toward a rotating black hole and you're climbing down a pole that's sitting radially, you are going to feel as you go in, you are picking up angular momentum, because if you had zero angular momentum, you'd be going around. So you're picking up angular momentum, and if you're just moving in a rocket, you've got to have rockets going off to the side, not only to keep you from going radially inward, but to keep you from circulating because of the rotation of space-time. If, however, you stop, so now you're at rest with respect to the black hole, but you're not moving in or out, you have angular momentum, and so you don't have to keep your rockets blasting. This is a mistake we made in the first edition printings of Exploring Black Holes. It is like a tornado, but it isn't like you experience a tornado. If you're hanging on to the post of your porch as a tornado passes over, you've got to keep hanging on, even though you're not changing your position. It's not true as you move in toward a black hole. You have to keep your rockets going as you move in, but once you stop, you've got the angular momentum you need. You still have to keep your rockets pointing inward so you don't fall, but you don't need sideways rockets at that point. So it's a very interesting combination of analogy to things like tornadoes and difference from things like tornadoes.
Oh, I was going to say something about dark matter. So do you guys all know what dark matter is?
Do you?
Well, okay, so I mean the basic idea is if you say look at a galaxy and you count up all the light that's coming from it, it's something like, let's see, and then you count up how much mass there has to be in order for the dynamics of the galaxy to work the way it is. We're missing a whole bunch of matter. So clearly there's some stuff there that's not luminous. I think it's something like
90%.
Yeah, I mean, it's the mass to light ratio is off by, a couple orders of magnitude. So it clearly can't be made up all of, say, stuff like the sun. So if you look at the luminosity of the sun and the mass of the sun, this is clearly not what is making up these external galaxies. So, I mean, you'll get probably more into this later on in the semester, but the basic idea is that of all of the matter in the universe, most of it is not luminous, it's dark. And in fact, of all of the dark matter, which we don't know what it is, most of it is even not made out of baryons. And so we really don't know what it is. I mean, if you go to physics colloquium or maybe even the more advanced seminars, this is frequently a topic for the whole hour seminar. What is dark matter? What is non-baryonic dark matter? Some possible ideas are maybe it could be partially heavy neutrinos. So we now think that neutrinos are not massless but have some small amount of mass. Those probably can't make up all of it, though. So even if that was some of it, you still need something else. There's other strange particles called axions that we haven't yet detected, but we think they exist just sort of from the theoretical point of view. It makes something else work out way nicer. Possibly primordial black holes. People talk about things called WIMPs and machos. So WIMPs are weakly interacting massive particles. And then, I don't know which order they happened in, but physicists come up with strange names. So, and machos are massive halo objects. Anyway, so there's it could be maybe supersymmetric matter, which again, we haven't detected any of that, but it certainly makes the theories work out better if it exists. We really don't know.
There's a cosmologist at MIT named Paul Schechter, and before a colloquium once I said to him, "Aren't you ashamed to be in a profession in which only 5% of what can be seen, in which all of the things you talk about, only 5% can be seen?" He said 1%. So it's about 1% of the things we see, and then we think we can make up from gaseous hydrogen and bits of neutrinos and stuff, we can make it to 5%. And then there's something like 33% dark matter, and then there's something like 67% dark energy, which is pushing things apart. And it gets worse since dark energy may have to do with the vacuum, and so it's the same as the universe expands, the same density, and so it's more important the bigger the universe is. It wasn't very important at the beginning. So this is I attended a talk at Harvard just before this, and he sort of outlined what we know about cosmology. And he said, we know what the parameters are, and we're beginning to get error bars on it, but the stuff itself, we think it's there, but we have no idea what it is.
I don't know. I think we're doing pretty good. We can see 90% of the way back to the Big Bang from, here on one little teeny planet in one little teeny solar system in one sort of average-sized galaxy. I think we're doing pretty good.
We're doing great, but there's plenty to do if you decide to go into this as a profession. Well, we didn't answer all the questions, but I think we're going to stop now. It's been you've been sitting here
but
for more
please
than
feel
an
free
hour.
to, if you want to come up and ask more questions,
Sure.
we'll stick around for a little while, so don't be shy.
Great. And the next meeting is on Thursday from 2:30 to 4 in 1273. Yeah, I think that's not a problem.